Hi, everyone. Welcome all to the next episode of our YugabyteDB Friday Tech Talks series. I'm Kannan Muthukkaruppan, one of the co-founders at Yugabyte. It's my real pleasure to welcome Raghavendra T.K. He usually goes by TK, and I'll let him introduce himself as well as the topic for today's session. So over to you, TK.
Thanks, Kannan. Hey, everyone. I'm TK. I'm one of the directors here at Yugabyte. Been at Yugabyte for about a year now. Prior to that, I've been working at Microsoft SQL Server for over a decade. So I have been working with databases for over a decade now. So the topic of today's discussion is packed row storage format at Yugabyte, right? Let's take a look at what is the current storage format in Yugabyte, right? Just checking, can you guys see my screen?
Yes.
Yeah, thank you. Row corresponding to the user table is stored as multiple key value pairs in the storage engine in Yugabyte. The storage engine in Yugabyte is called DocDB, which uses RocksDB storage under the hood for the storage of the actual key value pairs, right? So for example, let's take the table with the following schema with one key column, K, which is the primary key, and N non-key columns, C1, C2, and so on, all the way to Cn. And if you consider an example row with primary key K1, column 1, 10, column 2, 20, and so on, column N, 1000. If you look at the way this particular row gets stored in DocDB, we store them as key value pairs corresponding to the combination of every primary key and non-key column, right? So in this case, for example, it would translate into n key value pairs, starting with K1, C1 with the value 10, K1, C2 with the value 20, and so on to K1, Cn value 1000, right? So this is the current storage format in Yugabyte. So what was the motivation in storing in this way, right? So one of the fundamental things is whenever customers want to update individual columns, this scheme provides a benefit that you don't need to lock the entire row, right? So it provides a degree of freedom in the sense that you can have one thread updating C1 for the same key K1, while the other thread is actually updating Cn for the same key K1, right? And since they're not conflicting, they both can actually proceed in parallel. So it sort of allows for column level locking, and so which in turn provides a very good degree of concurrency, and so improved throughput for updates in general, right? As a result, even the amount of data that is read for the updates and the data that is written is also sort of reduced, right? So that was like one of the main motivating factors for choosing this particular storage format in Yugabyte. And it has served well for a lot of the YSQL, the Cassandra workloads for us till now, right? So let's look at some of the side effects of the current storage format. One thing that we have observed is even though we can put in prefix compression schemes to actually sort of like at the storage level, actually reduce the overhead of repeating the primary key n number of times. Even with that, we have seen the storage cost is slightly higher. And again, the other side effect is when you're trying to ingest a lot of the data, bulk ingestion being the use case, like be it the data for the first time or be it recurring data from IoT streams or other streams, the ingestion is not as efficient as it can be in some of the other schemes, right? Having talked about the current format,
And maybe TK, on the previous slide, it might be worth mentioning that while it's very update friendly, in general, like storing it as separate key value pairs also, causes a little bit of overhead in scan performance and so on, right? Like you're just processing through more data to do scans and so on. Yeah.
Right. Yeah. Good point, Kannan. I was going to talk about it in results, but yeah, I'm glad you brought it up now.
Got it. Thank you.
Yeah. Yeah. So with respect to what do some of the customers do to sort of overcome this format? So some customers who are sensitive towards either the bulk ingestion performance or some of the scan performance aspects that Kannan mentioned, they can actually go ahead and create what is called as user-defined types or UDTs, right? Essentially, they're effectively managing the individual columns at the application layer. And from the storage perspective, it boils down to a single key value pair, right? Like the primary key is still separate and all the non-primary key columns are clubbed into what is known as the user-defined type, right? So you can see that there are some side effects of using UDTs, although it can overcome the problems of bulk ingestion. One of the things is the docdb storage layer is not aware of the user columns, right? It just treats it as a blob of bytes. As a result, the updates to UDTs are not as friendly, right? So even if you want to update just one column, it results in read, modify, and update of the entire UDT, right? As a result, the locking aspects sort of like come into the picture, right? One of the other things that's important from Yugabyte architecture perspective is the query layer actually pushes a certain set of operators to the docdb layer in a bunch of cases, be it predicate pushed on like filters or be it aggregates and some of the other operations. However, for customers that have been using UDTs, the updates to individual columns cannot actually be pushed to the docdb layer because docdb treats it as a blob of bytes, and hence it also sort of like impacts the performance of updates, right? So that brings us to like, hey, why do we really need packed columns or a different storage format, right? I've talked about some of the drawbacks of UDTs. While UDTs solve some aspects, there are a few drawbacks. So we thought, hey, what do we need to do to sort of address it, right? So as we were thinking about it, one of the other things we noticed is customers, traditional SQL Server customers or SQL workload customers, they are actually used to the benefits of a packed format, right? Similar to the UDT format, because it takes very less amount of storage footprint. It's efficient for inserts, especially when tables have like very wide schemas / large number of columns. It also sort of aids in faster bulk ingestion of the data. Plus, a lot of the applications that are migrating from one platform to another, customers are hesitant in terms of like rewriting their application. Like if you go and tell them, hey, you rewrite with UDTs, like, hey, I don't want to change my application and things like that. So it's not necessarily an option for everyone, right? And especially for latency sensitive update workloads, UDTs is not necessarily an option, right? And that's the reason we sort of like came up with the packed row storage format, right? So how would the packed row storage format look like? It would look sort of like similar to UDT scheme that I talked about. Basically, one user row is stored as a single key value pair in the storage engine in docdb. So you have the primary key and all the non-key columns, they're packed together. This is similar to all of the packed row storage formats in various other storage systems, right? The benefit or the subtle difference between UDTs and packed columns is that the document DB layer or the storage layer is actually aware of the schema and is aware of the presence of the individual columns, even though it's packed together in the single row. So with this, we sort of have the best of the both worlds, right? And I'll talk about that in just a minute, right? Like in terms of like what benefits docdb, the packed row storage format in docdb provides, right? Now let's start with inserts, right? So when a user inserts a row, it comes in as a single key value pair, and so it gets stored as boom, just one row, similar to UDTs. The one thing about updates is that now that the docdb layer is actually aware of the individual columns, we continue to leverage one of the benefits we had with the previous scheme about locking the individual columns as needed by the updates, right? So if a if a query is actually updating just C1, then only that particular column is locked. And the update would actually look something like this, right? In this example, I've pointed out CN, like the query actually updated CN from 1000 to 2000. Then the update would actually produce the payload that is similar to the previous format, where we say, hey, column key value K1, column CN with the new value, right? So this sort of like brings in the best of the both worlds, in the sense that when we inserted the row, we inserted in the packed format. And when we updated individual columns, we are still benefiting from the aspect that we can lock individual columns only. And the update generates a payload that is as concise as just the update, right? It doesn't repeat the entire row as is, right? However, in the case of
TK,
update, sure.
yeah, basically exactly right in terms of this is a hybrid approach where updates can still be sort of stored vanilla unpacked, and both kind of saves in terms of still gives you the column level locking semantics, the finer grain locking semantic, but equally the other thing it gives you is avoids the read modify write overhead of repacking the entire row when you're just updating a few columns.
Thanks.
Yeah.
And the other optimization that would be made in the update is, like, in case all the columns of the row are being updated, then we actually do produce a packed format for that specific update, right? And we are sort of like continuing to see other optimizations around updates that don't necessarily update all the columns and so on, right? So this scheme, like Kannan mentioned, it's efficient in terms of updates and efficient in terms of storage as well, right? And in terms of like the selects, now, as you can see, if a row has updates, then the selects actually need to scan through all the versions of that particular row and construct the new version of the row that is visible to that particular scan. So the scan prior to packed columns had to go over n number of key value pairs. Now it only needs to go over as many versions of the non-packed key value pairs corresponding to that particular key, as well as the original packed row, right? So I talked about updates actually being pointed to that particular columns. So do we leave the system as is? The answer is no. We have a process called compaction at the storage level, which is actually traditionally responsible for compacting out different versions of the rows / getting rid of deleted rows and so on. So we enhance the compaction logic / scheme to actually produce packed versions of the row if it notices any trickled updates that came into the system, right? So as a result, even though the system could have accumulated several updates, over time, compactions would actually produce the compacted versions of the row, and this sort of helps with future scans, right? Now you can see, as a result, since we had to like take care of like packing and unpacking for scans and so on, the code is laid out such that it is like backward compatible, right? So our customers who were on previous versions of Yugabyte sort of are able to sort of move to the newer version and get benefit of pack columns without having to sort of like undergo an expensive upgrade step and things like that, right? So that was one of the benefits of, that was one of the things we kept in mind as part of designing the feature as well, right? So now that I've talked about the feature, let's go over some of the performance results, right? So this chart should...
TK, maybe one question. Will you be covering what it takes to enable this? Is it a table level property or things like that? Are you covering that little later?
Right.
Okay.
Yeah, I'll cover that a little later.
Okay.
Yeah. So with respect to the so this chart actually talks about the throughput of the bulk ingestion workload, right? So in this experiment, we ran copy. We were trying to ingest 1,000,000 rows, and we ran it with different configurations, right? So today, the bulk ingestion framework or the copy command supports two ways of running it, right? One, you can run it in a transactional mode where while copy is running, it sort of takes care of asset semantics with other concurrent inserts or updates in the system. There is another mode called the non-transactional mode, which is like the fast path, if you will, which allows copy to sort of like bulk ingest a ton of data without necessarily paying attention to the transactionality aspect compared to the other concurrent activity in the system, right? As you can see, without packed rows, non-transactional ingestion is definitely way faster compared to the transactional ingestion, right? So the x-axis showcased packed rows and without packed rows and with packed rows, and the y-axis is the time in seconds that it took to ingest 1,000,000 rows, right? And the other thing you can notice is as the schema gets wider, like when we go from 11 columns to 21 columns, it's basically one primary key and 10 non-key columns. And the second one is one primary key with 20 non-key columns. The time it takes to ingest sort of like scales quite a bit. And we've seen customers who have tons of additional columns, right? So you can see how this chart can continue to grow. However, when we got pack columns implemented and we retested it, we noticed that the amplification factor due to the number of rows is not as much as it used to be, right? So we bridge the gap between like, hey, if tables are wider, would the ingestion time increase linearly? We sort of like reduce that. And the other thing we reduced is we also reduced the time it took to ingest in transactional versus non-transactional mode, right? So you can see the difference between transactional ingestion and non-transactional ingestion is the gap is significantly reduced, right? For both 10 columns and 11 columns and 21 columns use case compared to before, right? So the other thing you can notice is pack columns is at least 2x faster. We have seen customers who have tried out pack columns be at least 4 to 5x faster in terms of bulk ingestion. And the fact that it has reduced the gap between transactional and non-transactional, we don't need to educate customers about, hey, there is this fast path, right? So they can just run copy just like they're doing it, right? The next thing I want to talk about.
TK, there was a question, maybe just to clarify what a non-transactional insert is, but it's good that there's less need to even use that code path if we get bridging the gap between the two. But yeah, if you could clarify that.
Sure. So so the copy command is it takes in different types of inputs, and one of the inputs is the CSV, right? So you can provide a CSV with say 1,000,000 rows and provide it to the copy command. In the non-transactional mode, what the copy command does is it accumulates a buffer of say 10,000 or 20,000 rows. It tries to insert it into the storage engine. If it succeeds, it's good. If it fails, then it doesn't care about the success of the previous batches, right? Any batch that succeeds is done. The next batch is picked up by DocDB, right? So the granularity of that whole insert is at the either at the batch level or at the row level. It's not like the transactional way of doing things. Like in the transactional mode, if you provide an entire CSV, then the copy command actually creates transactions internally for say 100,000 rows. So either all the 100,000 rows are inserted into DocDB or none of them are inserted, right? So so that is the non-transactional mode for copy.
Thanks,
The other aspect I wanted to discuss is about the storage reduction with the pack columns feature, right? So these charts actually show even with different types of compression schemes, the snappy compression and the zlib compression that's used on the SSD files, when we ingested about 2000 odd rows in a 1000 column table in the unpacked format and the packed format, you can see there's at least 2x reduction in the storage footprint, right? In fact, in some cases, like with zlib compression, the gain is actually slightly over 2x, right? So the storage aspect is not necessarily the only thing. If you look at the in-memory storage of the like the in-memory representation of these rows, in some cases we have seen it's like 5x better, right? Like the uncompressed format without the packed one is like 5x larger, right? So with that, I would like to just quickly showcase the two experiments that show the difference in size, right? It's basically the same numbers, but I thought I'll just quickly run through the thing if I had time. So in this demo, I'm doing the same thing. We are inserting into a table with 4 threads. Each thread is trying to insert like 500 rows, right? And it's a 1000 column table. On the right, I'm connected to an universe wherein the packed row feature is enabled. On the left, I'm connected to an universe where the feature is not enabled, right? As you can see, even though in both the cases we loaded about 1000 odd rows, you can see in this case, the compressed size of the SSD files is about 5 meg, whereas on the universe without the packed row, it's about 13 meg, right? And in this case, I believe I had enabled the zlib compression for the SSD files, right? So switching back to the slides.
So basically, just to recap, just to clarify, when we talk about the compressed format, that's the format that we're using on disk. So those are the on disk savings you will get, and how much depends on whether you're using Snappy or zlib. By default, Yugabyte uses Snappy compression. It has a little bit better trade-off, of CPU versus space savings. zlib you save even more in terms of disk space, but it has a little bit higher CPU cost. So that is one aspect. Then the last line that you see on both this terminal windows is if those blocks were to be brought into memory, into the Yugabyte processes block cache, then we handle them in the uncompressed format. And there you see an even bigger magnitude of savings with the packed representation, like 93 meg on the left side versus 18 meg. There is one question, TK, from the audience, which is like,
sure.
If you're accessing a subset of the column values on your queries, what is the additional overhead of using a packed row format versus non-packed format? So suppose you're just selecting C5 from that row.
Right. So even though the seek is on C5, even in the non-packed format, traditionally the way our lookup used to work is it used to search for the key within the SSD file. Now the SSD file is composed of sorted strings, right? So even though the scan is for key 1, column 5, the first lookup is for key 1 within the SSD file. So inevitably, all of the columns corresponding to a particular key would probably be in the same block of the disk. And when we need to fetch, we actually load up blocks into memory, right? So for the most part, for rows that actually fit within the block size, even though the seek is for a particular column, we would have ended up loading effectively the entire row, even in memory, even in the prior schemes, which is why the seeks with the new scheme don't necessarily pay an additional penalty today.
Yeah, so not only that, typically we are not going to incur more block cache misses. And in fact, actually, you're going to be able to hold much more in the block cache. But even if we were to assume that you already had the block in both cases, let's say the unpacked case and the packed case, even then, the way the packed row representation is, we can still efficiently get to a specific column within it using the column offsets and so on. So overall, in our experiments, there's very negligible overhead of this format versus the older format for extracting specific columns.
Right. And in fact, that's a good segue to the scan performance slide as well, right? So we actually were measuring the time it took to do a sequential scan of a table with 1 million rows, right? So on the y-axis is the time in milliseconds to select 1 million rows. And here you can see the different combinations that we tried with 1 key column and 1 non-key column, 1 key column and 5 non-key columns, and 1 key column and 10 non-key columns. You can see that, I mean, we do take more time with additional columns, but with packed columns, we have seen that the scans are like 2x or even more efficient, right? Like as the number of columns grow, our scans actually get better because of the reduced amount of processing that Kannan had alluded to earlier, right? So all in all, the new storage format, the packed row, is a win-win for most workloads. So then sort of like the question arises, hey, how do I get my hands dirty? How do I use the feature, right? So the packed rows is available as a beta feature in the release 2.15. So if you're using any builds 2.15.1 and above, you can try out the feature. The way to use the feature would be by enabling the tserver gflag YSQL enable packed row, set the value to true on the universe, and all the future tables on that particular universe will have the packed row feature enabled. There is an additional knob that you need not have to worry about, but for power users, you might want to take a look at it. Like it's called the YSQL packed row size limit. Basically, it can be used to limit the packed row feature for a certain set of tables, right? By default, this value is set to the block size limit. For rows over this size limit, we fall back to the previous scheme, right? This is essentially one of the limitations of, hey, how much memory we want to sort of like allocate for packing and all of that, right? So it has to do with the lower level nuances of the implementation. But at the end of the day, if certain workloads are seeing unnecessary issues with packed columns, then this is one of the ways to actually limit it to a certain set of tables, right?
So TK, one question coming there is, and maybe you're answering it in the next one, which is like, will this feature be enabled by default at some point in future versions, right?
Right. Yeah. Given all the benefits we are seeing, yes. So that is definitely on the radar. So with respect to the roadmap, right now we just released the first version of packed row features in 2.15. In terms of like the cross feature compatibility, we made it work with features like point in time restore, backups, and co-located tables. While we did make it work with Xcluster and change data tracking or CDC features, there are a couple of known limitations around Xcluster, especially around schema changes and how we interact with the packed row feature. Given that now the docdb layer is also needs to be aware of the schema changes, because it needs to, when it produces this packed row version, it needs to validate, oh, is it a valid schema version and things like that. There are some integration challenges there, especially with features like Xcluster and CDC, and that's the thing that's in works right now. The upcoming future release, 2.17, we plan to GA the feature and ensure that it works well with features like Xcluster and CDC. We also are working towards enabling the packed row support for the YSQL workloads. As of now, the feature is available only for YSQL workloads with the flag that I mentioned in the previous slide. And we're also looking at additional storage optimizations on the packed row format, right? For example, if you have a very wide schema with a lot of nulls, currently the way we store these rows, these columns it's not as efficient, especially if the values are nulls predominantly over a large set of rows and things like that. In fact, in some cases, UDTs sort of fare slightly better than packed row implementation when it comes to the storage cost of such rows. And those are some additional optimizations that we are thinking about for the upcoming release, right? So definitely our plan is to make it on by default.
Yeah, I think in terms of the additional optimizations that we could layer in a backward compatible manner, what you're referring to generally falls in the class of, if each of the attributes themselves is fairly small, then some of the how we represent nulls or offsets and so on, there is optimization potential to even get extract more. I did want to mention one thing on the previous slide, if I'm not mistaken. Just really wanted to call out, like, this is something we discussed, whether, hey, this is a table level property or not, and because the feature we've been able to implement it in a way with negligible impact in any of the cases, and in most of the workloads, significant performance improvement, we really decided that there's no need for it to be configurable. This is going to be the default storage format going forward. It is currently, because it's in beta, it's currently under a flag. And there are some cases of, like, when you're upgrading an older cluster to a newer cluster and you're doing rolling upgrades, we temporarily don't want to have a mix of servers that don't yet understand the new format and so on, right? So those are some of the reasons to make it under a control knob. But for new clusters on newer releases that start off their life cycle fresh, pretty much this will be on by default. So I wanted to call that out. And then the last point in this slide also, I think, let's say the block cache size, which is the default use for the packed row size limit, let's say it's like 64 kilobytes. I believe the scheme already handles the case that if you had individual columns that are much larger, those are stored unpacked, but then the remaining smaller columns on the brand new insert do get stored packed. Is that correct, TK?
Yeah, I believe so. But in terms of the thresholds, I don't remember the exact threshold we use for sort of like doing that split. But yeah, we do have that scheme in place. Yeah.
And I think there was one question maybe from when you were at the scan slide. I don't exactly remember, but the question said something like, what if I don't specify the primary key in the search and just want to select star from table on a non-indexed column? But my understanding is your example is actually similar to that. You're not relying on you're just doing a sequential scan on the table, right?
Right.
It will help those cases too, because you're just able to go through your rows much quicker.
And given that the storage footprint is smaller, you need lesser amount of memory to actually load in the rows, and then so that I think the combination of the space savings together with reduced CPU cycles to process the number of key value pairs, I think it helps with scans, not necessarily of with the primary key columns, but even the non-key columns. Yep, with that, I think, yeah, pretty much the end of the talk. Are there any other questions? Sorry, I don't have my...
No, I just wanted to echo that. Thank you very much for an excellent talk, TK, and also for driving a lot of this initiative in the team to make this happen. I wanted to share with the audience that next week we will not is a Yugabyte day off on next Friday, so we will see you 2 weeks from now. Wanted to thank everybody for joining the talk, and over to you, TK, for closing comments and to wrap up the talk.
No, yeah, thank you, Kannan. It's been my pleasure driving this project, and the pack column format, we can see how our customers are going to benefit tremendously, right? Both from a storage standpoint and even from a performance standpoint. So, thank you.
Cool. See you next in 2 weeks, and Frank Pechot will be covering table spaces in Yugabyte DB and kind of the cool things you can do in a cloud native database with table spaces when we bring in multiple zones, geographies, and partitioning and so on. So yeah, see you in 2 weeks.